Now, Dalton's law of partial pressures. Dalton said that for a mixture of gases, any container, the total pressure of these gases is equal to the sum of the partial pressures of the individual gases if they were alone. So now, a P total is equal to P1 plus P2 plus P3 plus etc. Depends how many gases are going to be mixed together. So if we have two gases and we mix them together, the total pressure of the mixture will be equal to the P1 plus P2. P1 and P2 are called the partial pressures of the individual gases. Now, looking at the expression here, we can say that P is equal to nRT over V. So we can replace every pressure by its expression. So this tells us that the pressure exerted by an ideal gas is not affected by the identity of the gas particles. The volume will not change because it's the volume of the container, and it's the same container, and the temperature will not change because all the gases exist at the same temperature in this case.
A container is filled with N2, O2, and argon gas. The partial pressures of N2 and O2 are 615 and 125 torr. Respectively, if the total pressure is 785 torr, what is the partial pressures which basically state that the total pressure is the sum of all the individual partial pressures, so that is the partial pressure due to the N2 gas, the partial pressures of O2 plus the partial pressure of argon. So every substance exerts its own partial pressure, and the sum of all these individual partial pressure is equal to the total pressure. Now, we're given the total pressure is 785 torr. We also have the partial pressures of N2, which is 615, and partial pressure of O2, which is 125. So now all we need is to calculate the partial pressure of argon. So we need to add 615 and 125, which is going to be 740. Next, we need to subtract both sides by 7. 4,785 minus 740 is 45.
Now, let's discuss the mole fraction. So the mole fraction is the ratio of the number of mole of a given component in a mixture to the total number of moles in the mixture. So the mole fraction of 1 is going to be equal to the partial pressure of 1 divided by the total pressure. So now, whether we have the number of moles or we have a pressure, we should be able to find the mole fraction of a gas in a mixture. Now, this is very important when we are solving a question on the gas documentary, since instead of working with the number of mole, we can just simply work with the pressure.
A 2-liter vessel holds 3 moles of nitrogen and 2 moles of oxygen gas. What is the mole fraction of N2 and O2? So let's start with that. If you want to find the mole fraction of substance, and it's equals to the moles of substance and divided by the total moles of substance, you can also calculate the mole fraction of substance. If you know the partial pressure and if you know the total pressure, since pressure and moles are directly related, that works out the same way. So if you want to find the mole fraction of nitrogen gas, we need the moles of N2 and we need to divide it by the total moles, which in this example consists only of N2 and O2. So there are 3 moles of nitrogen gas out of a total of 5 moles, because there's 2 moles of oxygen, so it's 3 out of 5, which is a decimal is about 0.6. So that's the mole fraction of N. Soon. So 60% of all the molecules in his vessels consist of nitrogen gas. The mole fraction of ozone is going to be the moles of all 2, which is 2 divided by the total, which is 5. 2 out of 5 is 0.4, so that the other 40% consists of oxygen molecules. So you can think of a molecule fraction as a decimal equivalent of percentage. Now let's move on to part B. If the total pressure inside the container is 1000 torr, what are the partial pressures of N2 and O2? So let's start with the partial pressure of N2. You can find it by taking the mole fraction of N2 multiplied by the total pressure. The mole fraction is 0.60. The total pressure is 1000, so therefore the partial pressure of N2 is going to be 60% of the total pressure, which is 600 torr. Now to calculate the partial pressure of O2, it's going to be the mole fraction of O2 time the total pressure. The mole fraction is 0.4. The total pressure is 1000. So the partial pressure of O2 in this example is 40% of the total pressure. So that is going to be 400 torr.
Gas stoichiometry. Using this law, we will be able to find or to calculate the molar volume at the standard conditions of temperature and pressure. The standard conditions of temperature and pressure states that the temperature is equal to 0 degrees Celsius or 273.15 Kelvin, and the pressure is equal to 1 atmosphere. If we rearrange the expression of the ideal gas law, we get V is equal to nRT over P. Now, if we replace these terms by their values and we can cancel the units, as you can see in here, we get the volume that is equal to 22.42 liter. Now, this is the volume of 1 mole of gas. We will call this volume the molar volume at the standard conditions of temperature and pressure. We can also look for the molar mass from the expression of the ideal gas law.
What is the volume of 2.5 moles of argon gas at STP? So what exactly is STP? STP stands for standard temperature and pressure. The standard temperature is 0 degrees Celsius, which corresponds to 270 Kelvin. The standard pressure is 1 atm. Now what you need to know is that at STP, 1 mole of gas occupies a volume of 202.4 liters, and you could prove this using the ideal gas law equation PV is equal to nRT. So let's plug in a pressure of 1. We're gonna calculate the value B. Let's replace N with 1 mole. R is the same 0.0, 8206, and the temperature is 273 Kelvin. So this will give you the volume, which 0.0 to 8206 times 273, and so you're gonna get a volume of 202.4 liters. So at STP, you can use this conversion factor. 1 mole of gas occupies 202.4 liters. Now, if 1 mole of gas occupies a volume of 22.4 liters, then what volume or 2.5 moles of gas occupy? So now, we could set up a conversion factor. So 1 mole of argon will occupy 22.4 liters, so the unit moles will cancel, and so it's just going to be 2.5 times 22.4, so the answer in this problem is 56 liters.
We know that the number of moles is equal to mass divided by the molar mass. If we replace this in the expression of the ideal gas law, we get that PV is equal to MRT divided by the molar mass. Now, or we rearrange it to get the molar mass is equal to the mass multiplied by RT divided by PV. In the similar way, we can do this with the density. So now we know that the density is equal to M over V. So the pressure is going to be equal to the density times RT divided by the molar mass.
Let's start with this problem 7. 0.723 grams of a gas occupies a volume of 2.4 liters at a temperature of 27 at a pressure of 1.8 atm. What is the molar mass of the gas? Let's start with this equation. PV is equals to nRT. Now N, the number of moles, is equivalent to the mass divided by the molar mass, and you can prove it based on the unit. The mass is in grams per mole. Grams is the same as G over 1. You can write it this way if you want. And then we're gonna divide it by grams over moles. So you can write this as G over 1 divided by G over moles. Perhaps you heard of the expression keep change. Keep the first fraction the same. Change division to multiplication and flip the second fraction. So notice that the unit grams cancel, giving you moles. So mass divided by the molar mass is equals to the moles. So what if I'm gonna do this? I'm gonna replace N with the mass divided by the molar mass. Let's use capital M to represent the molar mass. So we're gonna have PV is equals to M, mass divided by the capital M, the molar mass times 13. Next, I'm going to multiply both sides by the molar mass, so I have pressure times the volume times the molar mass is equals to mRT. You can put MW for molecular weight if you want to distinguish it from molarity. But however, you want to write this just to know that in this equation, it represents the molar mass. Now to isolate the molar mass, we got to divide both sides by PV, so the molar mass is equals to mRT divided by PV. So now we can answer part A. So let's plug in what we have. So we have the mass in grams, which is 7.723. We have the R. We have the R value, which we know it to be 0.08206, and the units are liters times ATM divided by moles times Kelvin, and then we have the temperature. It's 27 Celsius, but we need to convert that to Kelvin. So 27 plus 273, it's 300 Kelvin, and then we're gonna divide it by the pressure, which is 1.8 atm, multiplied by the volume, which is 2.4 liters. So notice that the unit liters cancel, the unit atm cancels, and also the Kelvin unit cancels, leaving behind grams per mole, which is the unit for molar mass. Now let's plug in the numbers that we have. So it's 7.7, 23 times 0.08, 206 times 300, which is about 190.12, and then take that result, divide it by 180, and then divide that by 2, divided by 2.4, so you should get a molar mass that equal to 44.1 grams per mole.